All right, so let's look at example 2 where it says birth weights of baby in the United States can be modeled by, again, the key words is a normal distribution. And it says this normal distribution has a mean, so we say X follows a normal distribution with a mean of 3250 and a standard deviation of 550. Those weighing less than 2,500 grams are considered to be of low birth weight. So first question says, what proportion of babies born are considered to be low birth weight? So the first thing remember we're going to do is we're going to label our curve, 3250. And low birth weight means they're less than 2,500 grams, which is somewhere out here. I want to be less than that. So I want to find the probability of having an X that is less than 2,500 grams. So we'll come here to Desmos. We'll go to functions. We want the normal distribution. Our mean is 3250. And put a comma. And then our standard deviation is 550. And if you want to see it again, if you press this magnifying glass, it'll put it in view for you. We want to find the cumulative. We want to be less than 2,500. So we can see that it's out here. The shading starts at negative infinity again. And it goes up to 2,500. And you can see that the proportion of babies that are considered to be of low birth weight is 0.0863. The next one says, what proportion of babies would your model predict as weighing more than 10 pounds? All right, and they give you that in grams because that's what you're converting to. So again, here is 3250. More than 10 pounds is 4,536. So look, if you want to be more than, you're here. You want to find the probability that X is greater than 4,536. So when we do this, again, we already have our mean and our standard deviation set. We need to set our bound. Our lower bound starts here at 4,536. And then it goes up to positive infinity. And you can see that is equal to, it's a very small amount, 0.0097. So let's go look at example 3. The time it takes a computer repair company to diagnose a computer follows again, the key word is a normal distribution with the mean. So X follows a normal distribution with the mean of 50 and a standard deviation of 12 minutes. The company closes at 4 p.m. every day. If the technician starts diagnosis at 3 p.m., what is the probability he will finish his diagnosis before he closes for the day? Well, if he starts at 3 p.m. and they close at 4, that means he has exactly an hour to get it done. So the probability that he will finish it means he has to finish it in X has to be less than 60 minutes. So we know our mean is 50. 60 is on this side of that value. We want to be less than that. Right? So it's probably we finish it before then. So we do this. We need to set our mean to, again, we'll go here. Function. Normal dis. Mean is 50. Standard deviation is 12. Find the cumulative. Our lower bound starts at negative infinity again. And we're going to stop it at 60. So there is almost a 0.7977 chance, or about an 80% chance that he'll finish it before the time is up, based on these numbers. There's only a 20% chance that he won't finish it. Look at the last one. The lifespan of a scientific calculator has a normal distribution with a mean of 58 months and a standard deviation of 10 months. The company gives a warranty of 36 months to replace any defective calculator with a new one. Suppose the company makes 1 million calculators per year. How many calculators may be replaced? So we know it follows a normal distribution. So X is approximately normal with a mean of 58, standard deviation of 10. They give a warranty of 36 months. So 36 months is about right here. Actually, probably be too much. It's about right there. So if you fall within this right here, if you're 36 months or less, that's when you get the warranty, right? If you don't get a warranty, you go past that. So I want to find the probability that X is less than 36 from this. So again, I'm going to need to go to my normal function. My mean is 58. My standard deviation is 10. I want to find the cumulative. I can tell you my lower bound is negative infinity. My upper bound stops at 36. So this is equal to 0.0139. So we're only giving about 1.39% of the calculators are going to get warranties, right? Which is why this works out. Now, if I want to find how many I have to place after a million, let's take a million. Let me use that. 1, 2, 3. There, do a million. Multiply it times that percentage, which is 0.0139. So out of those million calculators, I'm going to have to replace, suppose that you have a million calculators. I have to replace 13,900 of them.